All right, so once again, in this part of the unit, the second half of this unit, we're looking at thermal energy, which is a nice way of saying heat. Now, what thermal energy is all about is it's the total quantity of kinetic and potential energy possessed by the atoms and molecules of a substance. Because, and I think a lot of you, or hopefully some of you understand this part about solids, liquids, and gases, is that first of all, I have A, B, and C here where I go from solid, liquid to gas here. And a solid, there's very little space in between the molecules and they don't move very much. Where a liquid, again, the movement and the space between the molecules increases. And in fact, again, with the gases, molecules are able to move even easier. All right, now, the temperature, because that's what heat's all about, in which no movement of particles in any substance, whether it would be a solid, liquid, or gas, is called absolute zero. Now, I'm not even sure if there's anywhere in the universe that there is absolute zero, but I guess the closest would have to be Pluto, because Pluto's so far away from the sun. Perhaps there is places that does have absolute zero, but again, that is the case where no molecules move. Everything is just stably set. So even though we think it's really cold here, it can get much, much colder because absolute zero is called 0 degrees Kelvins, though. Or for us, minus 273 degrees Celsius, which is really, really cold, obviously, and we can't survive on that. Now, here's something that's really cool that I learned when I was, just teaching this class, is I didn't know this, is that we have the Celsius scale, which again, used in most countries, minus the US of A, and we have the Fahrenheit scale, which is primarily the US uses this. Now, the Celsius scale is based on the boiling point and freezing point of water. Okay, makes sense. Now, what I didn't know is the Fahrenheit scale is based on the boiling point and freezing point of brine, which is salt water. So Canadians, we base our temperature scale off of regular water. Americans, they go off of salt water. Now, there is two formulas because we're not going to deal with Fahrenheit because, again, we are Canadian. But we are going to deal with Celsius and Kelvins because Kelvin's a scientific number in which, again, it's 0 degrees. That's called absolute zero. Come on. There we go. All right. Click. So we have two formulas, as long as my computer here is going to let me do it. Hold on one second. This happened to me the other day, too. It's the first time. There we go. All right. So trying here. All right, there we go. So we got two formulas, or one formula, I should say, sorry, where we have our temperature, but in Celsius, because that's what we want to figure out, is equal to the temperature in Kelvins. But again, Kelvins is 273 degrees less than Celsius. And so again, this is Celsius, temperature in Celsius. Make sure I spell that right. I'm not very good with spelling, but that's a tricky word. I have more trouble saying Fahrenheit, so I'm glad I'm not American. And TK here would be our temperature in Kelvins. All right, now we get to example 1. What is the boiling point of aluminum if in Celsius, if it boils at 2,792 kelvins? All right, so this is, this here is considered our TK. All right, what we're looking for is our TC. All right, so I'm going to substitute in my formula, as long as my computer lets me here. All right, so what we're looking at here is we want our temperature in Celsius. Again, our temperature in Kelvin is 2,792. All right, and then we're going to minus the 273. Now, I'm lucky in this case because this formula is just a straight do the numbers, and aluminum boils at 2,519, again, degrees Celsius. All right, let's go the other way here. Example 2, what is the freezing point of oxygen? Yes, that can happen. If anybody's ever seen liquid nitrogen poured out of a jar, that looks pretty cool kind of thing. But you can freeze gases. Just generally doesn't get that cold because the freezing point of oxygen in Kelvins, in Celsius, is negative 219, which obviously we couldn't live in that because we couldn't breathe liquid oxygen. All right, so there's our TC. What we're looking for this time is the opposite, our TK, our temperature in Kelvins. All right, so again, I'm going to use my formula where my TC is minus 219, and that is equal to, again, my temperature in Kelvins, minus 273. All right, so this time I do have to do a little rearranging of my formula. I'm going to move this minus 273 over to the other side, and so it becomes positive. And so what I end up with is minus 219 plus 273 kelvins. All right, equals, or degrees I should say, it's going to be in kelvins, equals TK. All right, and in the end, if I put those numbers together, the temperature in kelvins makes it sound a little less worse, I guess, is that the temperature has to be, let's see here, minus 219 plus 273, 54, and it's kelvins. We don't say degrees. All right, we just say 54 kelvins. And that would be our freezing point of oxygen, which doesn't sound so bad until you realize it's actually minus 219 degrees Celsius. Still very, very cold. All right, and again, why we could never live at that temperature. We can't breathe it. All right, now, again, we're getting into heat. Now, heat is the transfer of energy from a warmer body to a cooler one. Since energy is moving from one source to another, there's a change in temperature. And most times what we want to know is how much heat or how much thermal energy is gained or lost by a body. And that symbol is a Q. All right, now there is a formula for the amount of heat in an object, and we're going to get to some of these variables. One of them's a little different, but the amount of heat an object has, because we can calculate whether it has some or none or how much it changes, is we have M, which is our mass. We're going to have this value C. Now that one's a little different. We'll get to that. And then we have a delta T. What am I going to put for delta here? Let's go with hashtag. A delta T. All right. So again, now M is mass. All right. Now C is called the specific heat capacity. And we're going to get to that because what happens is that every object holds heat a little bit differently. Some objects hold heat really well and some do not. And this delta T, that's a delta. I just had to use hashtag there. And delta in math and science always means change. So we have a change, and this is, because we're talking about heat here, temperature. All right, now let's get back to the specific heat capacity. Like I said, different objects hold heat differently, and that's kind of why we make certain items, like say a frying pan is made out of iron or a cooking pan is made out of glass, because they do not hold heat very well. Whereas sometimes we use other objects, materials, because they do hold heat really well. And here's what this specific heat capacity is all about. It's the amount of energy needed to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. All right, so that's what our specific heat capacity is. It's a measurement. I don't want to get into the units because they're crazy, but it is what you do need to know, though. It's how much heat does it take? Again, we're using standard units here to raise the temperature 1 kilogram by 1 degree. All right, so there's our formula. Q equals MC delta T. Now let's use this stuff. Let's see here. Example 3, a 500-liter hot tub. Now, again, here's a little something if you haven't taken chemistry. 1 liter is actually equal to 1 kilogram. All right. is at 20 degrees, which is too cold for a hot tub, no doubt about that. Now, the specific heat capacity of water is 4,180. And again, I'm not going to get into the units here. All right, but we want to look in is how much heat is required to raise the hot tub's temperature to 44 degrees Celsius. All right, which is about 105 Fahrenheit, 104 Fahrenheit, somewhere in there. All right, so again, looking at our variables here. Now, the first one is we know the mass. The mass of this thing is 500 kilograms, all right, because it's 500 liters. Our specific heat capacity is, and again, I'm staying away from the units here because they're crazy and they don't really mean a whole lot to us, right? Too much. It's 4,180, and I'm not going to ask for them either. Now, delta T, change in temperature. Now, we want it to be 44, and it's starting out at 20. So what we need to do is take our final temperature, TF, and minus our initial temperature. So in this case, we got 44 minus 20. And so in this case, we are looking to raise the temperature by 24 degrees. All right, and again, how much heat is required? Well, that is what's called our Q value. All right, so again, I'm going to use my formula where we have Q is equal to MC delta T. All right, so Q is equal to, let's see, we got our 500 there. Our C was big, 4,180. All right, or I guess depends on relative if it's big. And our change of temperature is 24. All right, so, well, this formula is a lot easier than a lot of things we've dealt with this year. And so I multiply those numbers, and I get, let's see, 50160, and then 3 zeros, 1, 2, 3. So let's see here. Whoops, go back. And what do we got for a number? Put some commas in there. 50,160,000. And again, because we're talking about heat, which is thermal energy, we got joules. So we have the same units we had before. So that's quite a bit of energy to raise the temperature of a hot tub, which generally takes about 48 hours. Miss my hot tub. All right, here we go. Example 4. How many grams of iron, which has a heat capacity of 450? And see how that number is already lower than water, because these are actually real values. These aren't stuff that I made up this time out. The heat capacity is a lot lower because iron heats up a lot faster than water does. Less energy needed per kilogram to raise it 1 degree. All right, so how many grams of iron, heat capacity is 450, would require 11,000 joules of heat to raise its temperature from 22 degrees to 40. All right, so again, getting down our values. Mass, we're going to have to find out, it says. That's right in the first bit. Our heat capacity, again, that's our C value there, 450. The energy, again, we're adding 11,000 joules of energy. All right, and let's see here. What else we got? Our change in temperature. So my delta T. All right, which again, we take our final temperature, we minus our initial temperature. All right, so if I take 40 and minus 22, I get 18. All right, so here we go. Going to substitute into my formula here. So again, I'll just write her down real quick. MC delta T. All right, so let's put in our numbers now. We got 11,000 joules of energy. We're looking for the mass here. Our C value is 450. And we already figured out our change of temperature there is 18. All right, so just simplifying things here. So I'm going to put together 450 times 18, and I get 8,100. And again, when you're multiplying, you can do in any order. So, and typically when you have a 8,100 times a symbol, well, then you write the number first. All right, and then divide by my numerical coefficient here. So I get my mass by itself here. So I'm going to divide by 8,100. So it's going to be 1 point something something here. All right, and so my mass, let's see here. I take 11,000 divided by 8,100, go to 2 decimal places, which it was good to see on the test. Everybody did that. I didn't see too many people rounding, very little rounding. All right, so my mass is 1.36, but again, we are in standard units here. All right, so this answer is in kilograms. And so if you want to convert from kilograms to grams, because that's what this question is asking, we have to multiply by 1,000 because there is 1,000 grams in a kilogram. And so there would be, let's see here, move the decimal place 3 to the right. We get 1,360 grams is the mass. That's how much energy would raise a piece of iron, pure iron, from 22 to 40. All right, let's see here. Well, we got one more here. Oh, we're rocking the iron again. All right, so example 5, a 50-gram piece of iron. So I'm going to have to switch that, right? Again, with the same heat capacity of 450, with an initial temperature of 547 degrees Celsius, loses 10,600 joules of heat. What is the final temperature of the iron? All right. So again, I'm going to go back and get my values here. So my mass is 50 grams. But again, I need it in standard units. So I'm going to divide that by 1,000 because, as I mentioned, there's 1,000 grams in a kilogram. And so I get 0.05 kilograms. All right, again, our heat capacity that's given to us, 450. Something you'll want to do is print off that formula sheet if you haven't done that, so the course formula sheet, because all the specific heat capacities are on there. So you're going to need those. Have them handy, so I won't have to give you a sheet. Let's see, what else we got here? It has an initial temperature, okay? So I'm going to call that TI is equal to 547. It's our initial temperature, and it loses heat. So when it's losing heat, we got our minus sign there, 10,600. Now in this formula, what we don't know also is the delta T. We'll get to that. Because again, delta T is TF minus TI, the final minus initial. All right, so again, time to substitute into my formula again, which we have Q is equal to MC times delta T. I'm losing 10,600 joules of energy. Whoops, let's get the units out of there. I always put the units in at the end. All right, I have 0.05 for my mass. My C value is 450. And delta T is what I'm going to be able to find out. All right, it's not what I want, but it's what I can find out, which in the end is going to help me find my TF, which we do want. All right. All right, so again, simplifying things here. So again, I still have this minus 10,600. All right, now I'm going to multiply my 0.05 times 450, and I get 22.5, and that's my delta T. Okay, just kind of like we were before here, where I'm going to have to divide by my numerical coefficient, 22.5. And I got a 22, whoops, 20, let's see if I can cover that up. There we go, 22.5. All right, and so my delta T, all right, now I got a negative divided by a positive, so it's going to be a negative number because, again, the temperature is losing heat, so I would expect my change in temperature to be negative. All right, so I do those, and I get negative 471.11 degrees. All right, now again, that is not my TF, because that's what we're trying to find here, but it is my delta T. So now I'm going to use the fact that my delta T is equal to TF minus TI. All right, so I have my temperatures minus 400, or my delta T is 471.11, again, going to 2 decimal places. It's equal to my TF minus TI, which I actually know, right? It's 547. Okay, well, second last step, I'm going to move that minus 547 to the other side. And again, when it changes side, it changes sign. So we're going to have this minus 471.11 plus that 547. That is going to equal my final temperature. All right, and so if I, let's see, well, add them together, or you look at it as subtraction, one or the other. My final temperature here is, let's see, 75.89, again, degrees, and because we're Canadians here, Celsius. And there we go. And obviously that is much lower than the 547 degrees Celsius. All right, so there again is a look at our thermal energy. All right, so we had two formulas. The first one being our, the Kelvins. And the second one being our Q equals MC delta T. That's our second one. Again, here's our first one. Our first formula where we have our temperature in Celsius equal to temperature in Kelvins minus 273. All right, so that is for